In this video, we're going to talk about correlation and regression, which are concepts that you'll find in sections 2.4, 10.1, and 10.2 of our textbook. Please access or print the guided notes to follow along with this video. First, we're going to talk about correlation, and the linear correlation coefficient, labeled R, is the number that measures how well paired sample data fit a straight line pattern when graphed. We use the sample of paired data, sometimes we call it bivariate data, to find the value of R, and then we use R to decide whether there's a linear correlation between two variables. And when we're talking about our two variables, think about your scatter plot, X and Y. We're only going to discuss linear data in this section, or linear relationships. Not all data has a linear relationship, but we will be sticking to in this course linear relationships. So that means we're looking to see whether our scatter plots approximate a straight line pattern, and then we're going to learn how to come up with a line of best fit to represent that straight line pattern. The first concept we'll discuss is correlation. Correlation exists between two variables when the value of one variable is somehow associated with the value of the other variable, and we're specifically looking for a linear relationship between the variables. Linear correlation exists between two variables when there's a correlation and the plotted points of a paired data set result in a pattern that can become approximated by a straight line. And now let's look at some examples. Here we have a scatter plot. You can see in the scatter plot, as X increases, the Y values also increase. We call this a positive linear correlation. When we're looking to see if we have a positive or negative correlation, we're always going to say, as X increases, what does Y do? As X increases, Y increases means that you have a positive relationship between your data values. And when we look at our correlation coefficient R, we're going to find that it will be a positive number. In this next graph, you can see that as X increases, our Y values decrease. If you find a graph that as X values increase, the value of the Y's decrease, then you have a negative relationship. And you can see here, R, our correlation coefficient, is a negative number. Sometimes you'll get data represented in a scatter plot where it's all over the place. You can't tell what happens as X increases. We can't tell what's happening to Y. If this is the case, we say that there is no linear correlation between our X and Y variables. And as you can see, when there's no linear correlation, this R value, correlation coefficient, is going to be close to 0. Here's another example where we have our values for X and Y plotted, and in this case, they make a pattern. But you can see that we have a low correlation coefficient at R equals 0.330. And we would say that there's no linear correlation for this data. It's not making a straight line pattern. Let me emphasize, this doesn't mean there's no relationship between the data. There's just not a straight line relationship. Looking at all of the graphs next to each other, we can see that they all have linear correlation coefficients R listed below them. It's a number that measures the strength of the linear association between two variables. For a positive relationship, you'll have a positive linear correlation coefficient. For a negative relationship, R will be negative. And it will be close to 0 if you have a nonlinear relationship. Let's learn more about the linear correlation coefficient formally. So it's called R, and we'll be finding it using our calculator. It measures the strength of the linear correlation between paired quantitative X and Y values in a sample. The requirements for linear correlation are as followed. We're going to use sample of paired XY data, and it should be a simple random sample of quantitative data. The questions you'll have in class, you won't always be able to tell whether you have a simple random sample or not. So next, what you would do with your data is you'd graph it, get a visual examination of the scatter plot to confirm that you have an approximate straight line pattern. Now, if there are any outliers, they should be removed if they're known to be errors. The effects of any other outliers should be considered by calculating R with and without those outliers included to see how they impact your data. We're talking about R, but let's look at the properties of the linear correlation coefficient more formally. Here you'll note that R is a number from -1 to 1 inclusive. So if you ever see a value from R that is outside of that range, you know that there's an error. If the values of either variable are converted to a different scale, R won't change. So the value of R is not affected by the choice of X and Y. So you could interchange your X and Y axis, and that relationship will be documented by R in the same way. R will stay the same. R measures the strength of your linear relationship. R is very sensitive to outliers, which can dramatically affect the value of R. So the closer that R is to -1, the stronger the negative relationship between the values. The closer R is to +1, the stronger the positive linear relationship between the values. And the closer that value of R is to 0, the weaker the linear relationship between your X and Y values. Take about 10-15 seconds to look at these graphs, and I want you to determine which one you think has the strongest linear correlation. Think you got it? The answer is C. It has the strongest linear correlation, and it'll be a negative relationship because as X increases, your Y values are decreasing. D has a positive linear correlation, and I would say that A and B wouldn't have a linear correlation. So their R values would be closer to 0. So we might say for A, we might have R equals, 0.1 or 0.2, and B might be similar. We're going to learn how to use our calculator to find the linear correlation coefficient R for data sets, but in the first problems you'll be given a linear correlation coefficient, and you'll have to determine whether it supports the data having a linear correlation or not. So on the next slide, I'm going to show you a table called the Pearson CCR chart, and you'll have that in your notes as well. And what we're going to do is we're going to compare R values to a particular value in that table to help us determine whether our data represents has a linear relationship or not. So using our table data, we're going to take our R value, the absolute value of it, and if it is greater than the table value that we find, we're going to say, yes, there's a linear correlation. If our value is equal to or less than our table value, we're going to say that there's not sufficient evidence to support the conclusion of a linear correlation. You can see here I have a table of critical values, and in your problem, it will say use a significance level of 0.05 or 0.01, usually 0.05, or an alpha level of that. That's referring to these numbers up here. So if it says use alpha equals 0.05, you're going to use this middle column here. And what you'll do is you'll match up your number of data items, and say you had 15 data items, with your alpha level, and you'll come up with a value in your chart. For this case, say I have 0.514. We're going to compare that to our R value to see if there is a linear relationship or not. Let's look at an example. It says here for a data set of brain volumes in centimeters cubes and IQ scores of 12 males, the linear correlation coefficient is 0.574. We're going to use the table available below to find the critical values of R. Based on a comparison of the linear correlation coefficient R and the critical values, what do you conclude about the linear correlation? In your notes, it specifically states it, but if a problem does not, you can just assume alpha equals 0.05 unless otherwise stated. So we're going to look in our Pearson table at alpha's 0.05, and we're going to match that up with n is 12. We can see that our table meets at 0.576. We're going to compare that with our R value of 0.574. So the absolute value of our R value is 0.574. We don't have to pay attention to the positive or negative. We can see that that happens to be less than 0.576. Our rules tell us that if the R value is less than the table value, there's not sufficient evidence to support the conclusion of a linear correlation. So in our example, we will cite that there is no linear correlation. When you're talking about correlation, there are some common errors you want to watch out for. First, we have causation. It's wrong to conclude that correlation implies causality. We've talked about it before. An important idea in this class is that correlation does not imply causality. Also, averages. Averages suppress individual variation and may inflate the correlation coefficient, so just watch out for that. Finally, linearity. There may be some relationship between x and y, even if there's no linear correlation. So we had looked at a graph before that had kind of a quadratic relationship. We would still have a weak R value there, and there would still be no linear correlation, but that doesn't mean no correlation at all. Please tune in to the next video to learn about regression and do more examples related to our correlation coefficient.